Hi, and welcome to this blog series around active-active Metro. Today, we'll be continuing our brief history of Metro in part 3, where we look at sidedness, witness, and APL versus PLD, whatever that means. So, we were looking initially at our mirrored configuration, where we have two data centers, a volume basically gets stretched by mirroring across, and the storage system makes it appear as if it's one big stretched volume local to any of the sites. Now, let's look at some failure scenarios. So, for example, an excavator digging through a line, basically cutting the mirror link between the two data centers. So what happens in that case? Both arrays stop seeing the other one. So the volumes get fractured. But what actually happened? Both of the arrays are unaware of the situation. Was the mirror connection cut, or is the other array down? Depending on that scenario, they would have to take different actions. But without any precautions, the only way to avoid split brain in this scenario is by disabling all volumes. Read-write access to all volumes disabled will ensure that there's no split brain scenario. Of course, that's not a really nice way of doing things. So whenever you build a Metro solution, you usually build each and every volume with a preferred site. So by basically tagging a volume as being preferred in one data center and non-preferred in the other data center, you basically make sure that if a failure occurs, then the preferred site will always continue and the non-preferred site will stop working. So this is what we call sidedness. So this is actually, in a more advanced way, sidedness also applies to the cluster, the stretch cluster that sits on top that actually runs the workloads. But here you have this certain sidedness to it. And of course, you could have the same sidedness the other way around in the same setup. So a different set of volumes may be non-preferred on the left side and preferred on the right side. So you always have preferred and non-preferred, or you can have preferred and non-preferred volumes on each site. Now, of course, if the mirror breaks, all non-preferred workloads will go to read-only, which also means that whenever you deploy a workload, you better make sure that you deploy that workload on a preferred volume. So this is where the cluster that sits on top, so in this case a vSphere cluster that sits on top, would actually also have to be aware of sidedness, right? Because it needs to make sure that a virtual machine running on the left data center in this case stays in the left data center, because it needs to be on the preferred side, on a preferred volume. Same thing for the other side. When you deploy a workload there, you better make sure that you also use a preferred volume in order not to lose I/O when disaster strikes. So this is a very basic way of avoiding split brain while being able to continue some of the serving some of the I/O for some of the volumes, right? AKA the preferred sites. We can do it in a slightly smarter way, and this is something that we've recently added to PowerStore as well. Because imagine another failure scenario. What if this storage array actually disappeared? It went offline. Well, the other storage array still doesn't understand what happened, right? It may be a breaking of the mirror, and the other array may still be alive. So by default, it would always disable access to the non-preferred volumes. But in this particular case, it may continue to serve I/O even for the non-preferred volumes, because the other array is actually down. And because the other array is down and it's not a break of the mirror in this case, it could actually resume I/O for everything. So this is where a witness comes in. When you add a witness to the system, the witness can actually see both of the storage arrays through physically different, through a different data path. And in this case, the remaining array can talk to the witness and say, hey, I just lost access. What happened, right? Is the mirror down, or is this array down? And the witness will tell the surviving array that, nope, I can't access the array as well. We'll assume, therefore, that the array is down, which also means that you can stop questioning yourself and you can just continue to serve I/O on preferred, and you can also continue to serve I/O on the non-preferred volumes. So you can imagine that this is a smarter way of doing things, but now it all starts to come down to the actual vSphere cluster that sits on top. Because yes, this one can continue to serve non-preferred volumes, but there's no workloads in this data center running on non-preferred. If you configured it right, and all the workloads always run on preferred volumes, that means that with the destruction of this array, all the workloads that were running here, they are preferred there, they will stop being able to run. The easy solution is when the entire data center failed, because then the vSphere layer will see that half of its nodes are gone, and it will actually recover those in the remaining data center automatically. And as this array also serves non-preferred volumes in this case, it would work. A more complex scenario would be, what if the array failed, but the servers didn't? So if it's just an array failure, now the cluster needs to be smart enough to say, hey, the workloads running here, they can't perform I/O anymore. They could perform I/O in this data center, so now I need to move them over here automatically in order to revive. So you can start to understand that it's not just a question of the metro layer, but it's also a question of the cluster that sits on top. That needs to be smart enough, and they need to somehow talk to each other or get an understanding on different failure scenarios. So this is the big APD versus PDL thing. You want to take a guess of what that means? Well, APD stands for all paths down, and PDL stands for permanent device loss. So APD is the most simplest form, all paths down. At some point, a workload can see a volume through different paths, and if all of those paths are down, the state simply becomes all paths down. So what the cluster does now, it says, well, all the paths are down. I don't know what happened to it. They may come back. So usually it will patiently wait for the paths to return. But at the same time, the metro solution may have decided and said, well, this array is down, right? And it's not coming back. So I told the other array through the witness that it can actually resume I/O on the non-persistent volumes as well. So basically, I need to signal to the cluster on top that something dramatically happened, and that is PDL. So PDL is a signal from the array that says this device has a permanent loss. So basically, the array telling you, hey, this volume just died, right? So perform some action to recover if you can, because this device is not coming back. And that is PDL. So PDL is actually a SCSI state that is sent up through the cluster or to the cluster, to the vSphere cluster. And as you can understand, it needs to actually grasp the idea of PDL in order to be able to recover from that. We'll be trying that in the lab and see what it does and how it works, but it does complicate things. So when you look at it, right, all paths down, PDL, once you got that understanding, you will start to understand that building a decent metro environment is very hard. Actually, it's taken years for Dell EMC and VMware to actually get on this path and make it work as it works today. It's pretty complicated. You could also understand that Kubernetes is a long way from getting up to this level when we're talking about enterprise readiness and metro solutions and stretching Kubernetes. The reason that I highlight VMware here, because that is more or less a finished product, right? We've taken all of the big problems and solved them in that world. So, well, up next, of course, is the world of containers. I don't think there's any more complexity except maybe for the networking layer, because I didn't talk about networking, but you can imagine that as you can move workloads around, the different WAN connections and the sessions that are running through the different WAN connections can give some some complexity as well. I won't be highlighting them in this series, but I will probably have a guest blog post on that pretty soon. So next time we'll be looking at the lab setup and see how we got it set up, and after that we'll try and break stuff and see how that performs. For now, thank you for watching and stay tuned for the next one. Bye bye.